Yeah, this was only the introduction, so I think it's fine if I start here again. Yeah, as identified by this survey I cited here, there is a huge demand for easy to tune or even auto-tuning algorithms for the client neural networks instead of optimizing only the communication protocol and aiming at a good global accuracy. And secondly, and maybe more obviously, federated learning scenarios inherently generate a large communication overhead by frequently transmitting the data between clients and servers. So there are two basic concepts to reduce this amount of data. First, reducing the frequency, or second, by compressing the data to be transmitted. However, often those methods slow down the overall training process, or they require an increased number of iterations to achieve a converged state of the system. Or they achieve a poorer performance due to the divergence of the different client models. This leads to the ultimate goal of our proposed framework, or even generally of federated learning, that is that we do not want to compromise on convergence speed due to the compression of communicated data or the reduced frequency. And we want that the clients can fastly adapt to the local data splits if they have prior knowledge, which is often true. So we come up with the idea of filter scaling on top of a compression pipeline, which implements only one extra trainable parameter per convolutional filter to compensate for the trade-off of this data compression and learning progress. We hope with this additional trainable parameters that there's an increased model capacity on the one hand side, but also that fine-tuning happens to the filters. And with this fine-tuning, that we can also adapt faster through amplification and suppression of some convolutional filters on the client sides. So they can amplify more important features for their data, or even suppress the unimportant features. How did we implement it? It's pretty much straightforward. So when you check the formula for standard fully connected layer or convolutional layer, here we depict the output for fully connected, which is scaled with a scalar scaling factor, or the output feature map of a convolutional layer, which is also scaled with a scalar. Having then equipped, and it's, by the way, easy to implement from a software perspective, where we search the model and just replace the standard convolutions with the scaled version. And yeah, maybe one important thing, it's important to add the bias or batch unfolding afterwards. And having then equipped those layers with the additional scaling factors, how are they trained? We first compute the forward pass, and where the scaling factors are initially set to 1. Then we compute a backward pass and update only the weights. So we ignore the scaling parameters. Then we would compute the difference of the new state minus the prior state, and start with our compression cascade, where we apply some specification, quantization approaches, and entropy coding. I don't want to go too much into detail here, but yeah, what is maybe interesting is our entropy engine, coding engine, which is Deep Carbag, which was used for video coding, but is now used for, or adapted for, decoding of neural network data. And it's part of the ISO-IC standard, which will be released this year. And we also put some, or contributed to it. Then we use this compressed sparse weight update and add it again to the prior state of the filters, compute another forward pass and another loss, and backpropagate this loss to update only the scaling factors. Now we put all of it together into one into a federated learning scenario where we would have n clients which are updated in a average federated average fashion. Only that we send the model differences here, compressed and scaled, of course. And what we then obtained is that, for example, here in MobileNet v2, that the scaling factors behave different from layer, from the location of the layer within the neural network. The output layer, for example, is only amplifying the scaling parameters, whereas in the more shallow layers, they don't change much. Most of them, the blue curve is, by the way, the mean value. They are around 1, which means that they have no great effect on the output. However, in deeper layers, they can pretty much amplify some features or even suppress or cancel out others, which is particularly advantageous in computer vision. Another side effect of this kind of scaling is that we observe sparser weight updates, actually. And as you can see here, throughout the training epochs, in the later epochs, there are some cases of the scaled filters where only the scaling parameters are transmitted and not even the weights anymore, compared to the unscaled version, which is the blue and the orange bars here. And we think that this comes from the gradients associated to sparse feature maps, which are sparse due to the scaling factors. And yeah, also that the filters may be converged kind of due to the macro training through the scaling factor, which means they don't change much because the scaling factor did the job already. Now, let me show you some main experimental results. Here, we trained the federated learning scenario on Pascal VOC, and our each data point here shows one communication round and the cumulated sum of data and the achieved global accuracy. So if our goal is to have fast and data efficient federated learning, we want to shift those curves to the top left corner, right? And this is what we achieved here, where we tested 3 different learning rate schedulers for the scaling factors, and the blue curves are the baselines. This is same, but we only updated the classifier part to check if this also is beneficial. And as you can see, these 3 curves are for the end-to-end case, and those curves over here are updating only the classifier, and this is the classifier including scaling factors. It's only 258 scaling factors with a big influence. Finally, some comparative results where we compared ourselves against federated averaging with Kaba compression and sparse ternary compression, which is the same as federated averaging, but having only ternary weight update elements and a sparsification rate of more than 96%. And as you can see, in all of the cases, we meet a good trade-off between fast and efficient federated learning. And compared to federated averaging, we achieve higher top 1 accuracies and smaller data transmission. So to conclude, we presented fast converging data efficient framework for FL in CV applications, and the compression pipeline applies state-of-the-art sparsification, quantization, and entropy coding. And we equipped weight layers with additional scaling factors, which then amplify or suppress the impact of specific filters. This results in an overall reduction of the transmitted bit streams. And the proposed method was tested with different FL settings and architectures and data sets. Thank you very much. I'm glad to answer your questions.